Hey there, class. We're going to get into Unit 7 here today, and this is our unit on rotational kinematics and dynamics. So really to start off with this, I want to get into a quantities comparison, and this comparison is going to be between our linear or translational. Pretty much everything we've dealt with this year has been linear or translational, and compare that with angular. The angular is going to be things kind of rotating in circles. So we'll take a look at that and hopefully see that these things really are synonymous. So first of all, we are familiar with the concepts of displacement, velocity, and acceleration. These are, of course, all vectors that we understand that have the various units. Notice in the angular side of things, we also have similar things here as well. Where this is delta theta. Delta theta would be a displacement of a circular thing. So if we can imagine a circle and, I don't know, imagine some point on the circle, and this entire thing rotates through, and typically I guess I use red for kinematics quantities. So if we could imagine this, this point, imagine it rotated through some point like some rotation like that. Pretty much our angular displacement, okay, is kind of like this delta theta. It's a change in angular position, just like a displacement in the linear sense is a change in an actual position, kind of in the Cartesian coordinates. We have our angular velocity. This is the small letter omega. The large letter omega, of course, is the horseshoe-looking symbol. And angular acceleration, this is the Greek letter alpha. This is the small letter alpha. The corresponding units here are in radians, radians per second, and radians per second squared. Again, you should notice the similarities between meters, meters per second, and meters per second squared. Okay, getting into angular dynamics. Again, analogous to mass in our linear dynamics, again, think of this as the inertia that keeps an object from moving. This is what Newton's first law describes as an object will tend to stay in motion or resist changing motion. This is the inertia. Well, in angular dynamics, the equivalent would be what we know as the moment of inertia. I sometimes call it an angular mass, although it really is more correctly called the moment of inertia. This does have some strange units here, and but nonetheless, those are its units. To make a mass accelerate, we need to apply a force. In similar fashion, for an object, say, this rotating thing here, if it's going to accelerate, if it's going to have some angular acceleration alpha, we need to apply what's called a torque. Okay, and a torque would be due to the fact, let me get a blue marker here, would be due to the fact that we apply a force on this edge of the rotating thing here. Let's say it rotates about some center of mass right here. So this force that's applied here will induce what's called a torque, and that torque would be measured in a Newton meter. What results if we have a torque applied to something that has an angular mass or a moment of inertia is, of course, an angular acceleration. So again, we have the equation that we're very familiar with in linear dynamics, that the sum of forces equals mass times acceleration. Well, in the angular side of things, we're going to have a very similar looking equation, and that's the sum of torques has to equal the angular mass, i.e. the moment of inertia, times its angular acceleration. Just a note here real quick about torque and angular acceleration. They do in fact have They do, in fact, have directions. That's a little bit outside the scope of this class. Typically, if I draw them, you're going to see me drawing things like this. It has to do with something called the right-hand rule. We're not going to get too much into that here. But again, just note they are, in fact, vectors, and therefore they do have magnitude and direction. All right, the last quantity that we probably are familiar with here is the idea of momentum. And again, in linear momentum, we use the Greek letter rho, and its units are Newton seconds. We have, oh, this is a typo. This should not say angular acceleration. This should say angular momentum. And we use an L, and again, it has units of kilogram meters squared per second. So it's not exactly a unit that flows off the tongue, but nonetheless, this is our unit for angular momentum. So when it comes to equations, you're going to see here, again, there's synonymous equations with the force. Again, what we're familiar with is force equals mass times acceleration. The angular equivalent to that would be the sum of torques equals the moment of inertia times the angular acceleration. Likewise, when we deal with just the kinematic side of things, when we talk about an average velocity, that's going to be found in the rotational side by an angular, again, an angular velocity. The average angular velocity would be its displacement in the circular fashion. Okay, again, a circular displacement or an angular displacement divided by time. Likewise, it should follow that pretty much all of our familiar equations in the kinematics have their equivalent in the rotational side here as well. So again, these are all familiar equations because we've used all of these pretty much this entire year. We now will look at this from a rotational side and see that they're very similar. Something that's a little bit new here is that we can take something that's rotating in a circle and I'm going to use the word convert, but effectively you can find out how far it's moved. So again, we can, if you can imagine a circle, and that circle rotates about some center of mass, and it has some, again, let me get the right color here. It has some angular displacement. Okay, that's actually going to, if you can imagine this rolling on the ground, that object will actually end up moving some distance. Okay, it'll actually end up moving here, and that would be what we call its linear displacement, right? Or what we know as just displacement. And that can be found by taking r, in other words, the radius of our object times the angular displacement. Now, if you really think about what this actually is, this really is just arc length. Okay, I'm sure in some math class at some point in time, you learned that the arc length was equal to r times the angular displacement, or again, you would have probably just said the angle here. Okay, without showing any derivations, it should also follow that the tangential velocity, or the velocity of a point, if we were to take a look at a point on this edge, its velocity at a tangent, that's this velocity t, would be equal to r times the omega. And likewise, it should also follow that the tangential acceleration, that would be, again, along a tangent, it would be r alpha. All right, so let's talk about three types of accelerations. So we just briefly mentioned here this idea of tangential acceleration. That's this idea, if you look at a point, how is it changing? And again, this is kind of the familiar one that we have. We've also talked a little bit about the radial acceleration. Okay, the radial acceleration, again, if I take a look at an object, the radial acceleration would actually be that center seeking. Okay, we've again used the word centripetal for this. and this being our normal, I guess I don't really call it normal, but the linear acceleration. And then lastly, this puts also in what we call the angular acceleration, and that's again this alpha, which again I'm going to draw or represent as a kind of a curved vector here, alpha. So we can kind of think about these three types of accelerations as a tangential, which we're familiar. This is the linear acceleration, the radial acceleration, which again is corresponding to a centripetal acceleration, and the angular acceleration. This is kind of our new one. Okay, so if we put a star beside that, that's our new one, and this is how quickly this is changing its angular velocity. Okay, so I'd like to finish up there for today. This was simply to compare different quantities that we are familiar with and show that they actually are going to be very similar to the quantities that we will deal with on the angular side of things.